Here we have a graph of y equals the secant of x. In the last video, we graphed y equals the cosecant. This is the secant of x because it mirrors, in a way, the cosine function. This is the graph of the cosine function here as far as we can fit it, as much of it as we can fit on the screen. When x equals 0, for the cosine, y equals 1. So we can tell that this is the cosine and not the sine because it starts up, comes down to -1, goes back to +1. It doesn't really start here as much as we tend to start with, when we graph, we tend to start with x equals 0. And so this is sort of the first value that we graph, but it doesn't actually start anywhere. It goes on forever in both directions. It takes 2 pi to graph one full cycle of the cosine. Now, we're not interested in the cosine here as much as we are at the secant graph. The cosine graph we know pretty well. The secant graph is related to cosine in the same way as the cosecant graph is related to sine, where the function cosine is equal to 1, 1 over 1 is also equal to 1. Where the cosine function is equal to 0, we have 1 over 0 for the secant graph, which means this is an asymptote. So it has exactly the same features as the cosecant graph, but it's shifted over. Remember that the cosine graph is just a shifted over graph of the sine graph as well. We can graph variations of secant and cosecant just as easily as we can sine and cosine and tangent. I'm not going to spend a lot of time on this because we've already spent quite a bit of time looking at trigonometric functions and then looking at transforming their graphs. So I'm just going to pick a few critical points on the graph of cosine. And let's see, we'll do when t equals 0, when x equals 0, when x equals pi over 4, when x equals pi over 6 and pi over 3. And let's note that there is also an asymptote at the moment at pi over 2. Now, again, as I've done many times in the past, we need to rewrite this function so that it says the secant of, and we're going to factor out the 2. That means dividing a 2 out from 2x and dividing a 2 out from pi, right? In this case, there's no vertical shift and there's no stretch factor. All right, I've gone and got more accurate measurements for pi over 6, pi over 4, and pi over 3. And I've made a mark on the graph for each of the output values for the secant, not the cosine. Cosine value would be here. But for the secant function, when x is pi over 6, the y value, the output value is 1.15, and I've made a note of that here. At pi over 4, it's 1.41, and at pi over 3, it's 2. Now, if I'm going to graph this function, I need to take each one of those points and shift them to the right pi over 2 units, and then I need to compress the graph so that there is room for 2 periods, 2 cycles in a 2 pi region of the graph. Remember that period is how long it takes to get from one end of a cycle to the other end. In other words, it's how long it takes to do one cycle. If I went beyond 2 pi, I'd be starting a new cycle. Well, it doesn't really look like it here, but that's how long it takes for secant as well. If I think of this as my starting point, the graph starts at 1 and goes up, behaves asymptotically, it comes up from pi over 2 to pi, and then it goes back down again, and then behaves asymptotically coming down from positive infinity until it gets to positive 1 again. And at that point, the cycle starts to repeat. It goes up, and then behaves asymptotically, and so on. So it still takes 2 pi to repeat a cycle for the secant graph. The same is also true for the cosecant graph. I didn't talk about that there. So it still has a period of 2 pi, and we have to squeeze that into half of that because we need to make room for 2 copies of the graph in the same amount of space. We're going to start, though, with the horizontal shift. And all I'm going to do is move the points or redraw points pi over 2 units to the right and then connect them. This point will be moved to here. This point will be moved to here. And this point will be moved to here. Now, I'm going to graph this part of the secant function because it matches what we consider one full cycle of the cosine function starting where x equals 0. It's not uncommon, however, to see instead, for example, this part graphed or shifted because that still encompasses a 2 pi wide region of the graph. X goes from some value to 2 pi larger than that value. And it's a nicer piece, I think, of the graph to include, right? We don't have these sort of half curves here. I'm going to stick with the half curves just because it matches this part of the cosine graph that we know so well. But know that you may see it graphed a different way. And in fact, if you choose to do it this way, then I'm fine with that. So the first thing I've done is I've moved each of these points that has a value of 1 or -1, pi over 2 units to the right. We can notice that wherever there was an asymptote before, that can be moved pi over 2 units to the right. You can see asymptotic behavior on the original graph here, so I'm going to move this asymptote pi over 2 units to the right and put it here. And then as you can see, I've added some other points, moved them pi over 2 units to the right. And you can see that this half graph, and this graph here, these are not complete graphs. This half curve, I should call it, and this half curve and this curve here now constitute the graph of, let's write it in up here, y equals the secant of x minus pi over 2. Doesn't show up very well on a dark background, I apologize, but it's blue and that matches the current graph. I'll do the last one in a lighter color. So now that I have my graph shifted, I've done this piece. I need to figure out what the period is and put this part of the graph into a region of the graph that's that wide. So I can either cut everything in half and try to squeeze two, let me get a different highlighter color, squeeze 2 copies of the graph into this 2 pi wide region of the axis of the coordinate plane, or I can figure out what the period is and graph one cycle in whatever that is. I know it's going to be half of that, just because I know I can get 2 copies in one stretch, then I must be able to get 1 copy in half a stretch. But let's go ahead and do the period piece. Because we're working with secant, which is related to cosine, we know our period is 2 pi. So we're going to take 2 pi and cut it up into b equal parts. In this case, we know b is 2. So we replace b with 2. We simplify, and we learn that the period of the function we're actually trying to graph, this one right here, is pi. So if I want to start here, and I have to because I've had to shift the original graph over, I want to start here instead, then I need to squeeze all of this into, let's see, I think I'll use pink, into a pi wide part of the plane. So instead of having asymptotes here and here, I'm going to have them here and I think here. In this case, I think the easiest way to go about it is to cut all of these distances, if you will, in half. So I think because it's an easy number, right? It's a very easy number to work with. So I think that's what I'm going to do. I'm going to take each of the distances away from the starting point, which is pi over 2, and cut it in half. Well, this distance was pi over 6. And then the next one, here, I'll go from here. This distance was pi over 6. This distance, the distance to here, was pi over 4. And the distance to here was pi over 3. So pi over 6 is going to become pi over 12. This point right here needs to move over here. What color shall we use this time? How about pink? Right, so at this same height, I'm going to put a point halfway between where it is and where we started our graph. So halfway, and then I'll do the same thing for this point, which means it's going to go about there. And this point moves to about there. And as you can see, that makes our graph a lot skinnier. In fact, it's also going to move our asymptote to halfway from where we started the graph to where the asymptote was. So I actually need my asymptote to be here. Now, as a reminder, asymptotes are not actually a part of the graph, but they can be very useful guides. So I'm going to go ahead and put that in. Now with this other asymptote, it's going to be halfway as well. I started the graph here, and my asymptote is here. Halfway between those is here. So I'm going to have another asymptote this section of the graph here now has to fit between these two asymptotes. This point gets to moved to here because it has to go halfway between where it is and where we started our graph. And so this part of the graph has to fit in here, but it also has to start here. And our last piece, we can kind of think of as starting here. 5 pi needs to fit inside this region here, right? So we can think of the width of the graph as being 5 pi over 2 minus pi over 2. That's 4 pi over 2. That's 2 pi. Half of that distance is pi. So I need to go back pi from here, and that is 2 of these boxes. So this graph right here is actually going to start here. So let me put a point there and finish up the values. Again, I'm taking them from about halfway where they would have gone. And I can finish my graph. Now, as I've said many times before, I'm not an art teacher. It's hard to follow what's going on here. It's hard for me, even though this is my own work, to track what the final result is, to see what happened from one stage to the next, So for that reason, I've actually also highlighted my final answer here. In an assessment setting, there are a lot of different ways you can sort of accentuate your final answer. One way, for example, would be to use very fine or very faint lines, not too faint because I won't be able to see them, on all your intermediate answers, and a bolder, darker line on your final answer. Another way would be to use colors like this. Another way would be to use dotted lines instead of solid lines, although that gets tricky with these curves. Let's see, what's another way I thought of? Oh, you could do individual graphs for each one. Instead of putting them all on the same grid, you could do separate graphs for each transformation and then put your final graph on a separate piece of paper. So there's lots of different approaches. No one is better than the other, they're just different. I did this one quite a bit more quickly. It took me about half the amount of time, and I did a lot of the steps sort of off camera, if you will. But I hope you can see the process is the same. You start with the graph of the original sort of toolkit functions, and then you, in order, do the transformations to that graph that you need to in order to get to the final answer. So that's our process, and we're going to look at one more graph, and I think I might not even do the graphing variations part of that, or maybe I'll kind of squeeze it in at the end instead of making a separate video for it. So that's it for graphing variations of secant and cosecant. We have one more type of graph to look at, and that is cotangent. So we'll talk about that next.